Okay, sorry for delay. Today, we're happy to invite Professor Sang-pyo Kim from Kunsan National University. He will today talk about the compact astrophysical object with magnetic field. Please start.
Thank you for kind invitation. Particularly Stefano and Wontae and Professor Herman Lee is joining online, I suppose. It passed more than a year since my last seminar here last February. I gave a talk on reflectionist quantum mechanics, surge quantum mechanics, reflectionist potential, surge quantum mechanics, and KDB, solid tensing. That is kind of special feature of strong field electrodynamics. Now, today, just because Stefano and his group, Arpan and Hyomin and I are working on applying this black hole physics to dark matter, or the other way, dark matter in the context of black hole environment. And the new result published today in JCAP. So I suggest actually this seminar more than a month ago when I was in Taiwan to collaborating with my friend Chang-Mei Chen. That is actually what I want to address today, just because I hope to apply the black hole physics to the dark matter research. Let me begin with what we mean by some terminology about compact object. Usually compact object in general relativity means black holes or the neutron star or magnetar. Magnetars are special kind of neutron star, highly magnetized neutron star. But these are really, it has high density in terms of the mass and volume. So the density of mass per volume, the mass density, that is really high. So we call, in general relativity, compact object. But in astrophysics, a little bit more abstract sense. So we very well understand about the black hole physics, the black hole solution. There are the thermodynamical properties and the quantum properties black hole better than the astrophysical black hole in real environment. That is magnetic field. We do not have the analytical and explicit solution of black hole with magnetic field. That is a challenging problem, but in real astrophysics, black holes are surrounded by the plasma environment. Well, it has magnetosphere. It has magnetic field. Now, how to describe this highly compact astrophysical object with the magnetic field in general relativity? That is a challenge, but this challenge has lasted more than a century. Nobody succeeded. I will tell you about that. Now, the other problem, black hole, because of no-hair theorem, that is simple, really simple. It has mass characterized by mass and charge and angular momentum, the rotation, and radius of ds and abs. I'm talking about 4 dimensions. Because of them, then this no-hair theorem state that black hole does not allow multipolar magnetic field. But in reality, as I said, we have magnetic field, the threading were coming from the magnetosphere. They are how to make it consistent and consistent theory in general relativity. That is a real challenge. On the other hand, the neutron star magnetar, we understand its physical properties. It's a really high density matter. It's a kind of some huge atom, the astrophysical scale atom. And we have a better understanding of our equational state and more better understanding of magnetosphere. But real challenge is that how do we describe this neutron star or magnetar within the framework of general relativity, just because this compact object rotate. So we need a rotating space-time geometry. And just because different from the black hole with no Hale theorem, now it has equation of state. There's no horizon. So we have to incorporate equation of state of matter on the right-hand side of Einstein equation, together with magnetic field. That is more challenging, very complicated. Only numerically we can do. But there are some the approximation that we approach the relativistic description of this neutron star. Just assume the magnetic field is weak enough. I mean, the energy density of electromagnetic field is small compared to energy density of neutron star. That is assumption. Then just introduce a rotating geometry and weak electromagnetic field. But from our terrestrial experimental viewpoint, the magnetic field is far beyond our own achievement, actually, even the above critical field. So in general relativity, simple. Now, actually, the diagram actually summarize all possible physics. We can have the strongest magnetic field in the universe. So that is magnetar. By magnetar, usually we classify any highly magnetized neutron star magnetic field stronger than critical field were close to. So 10 to the 13 Gauss were above. The highest magnetic field observed so far, that is 10 to the 15. And according to some theoretical model calculation, magnetic field in the center of neutron star or magnetar 10 to the 18 Gauss or more, that depending upon nuclear model that generate its magnetic field.
Sorry, how do you define the critical magnetic field?
Oh, actually, yeah, critical field means that lowest Landau energy level, lowest Landau energy equal to less mass of charged particle. That is the critical for the charged particle itself. The lowest mass charged particle, that is electron in our standard model, that gives 4.14 times 10 to the 13 Gauss. Now all shown here. Now this magnetar and the pulsar are lower than that. Actually, probably this also, this is a review article. They aim to be covering whole particle physics, grand unified, just because all unit in Planckian scale. So it has very small, in Planckian scale, the magnetic field is 10 to the minus 16. And the magnetar has 10 to the more than 29 Tesla, that is 13 Gauss, but in Planckian scale, still lower. But actually, yeah, the reason they show this diagram even imitation scale, electroweak scale, and Planck scale, just because they have in their mind kind of the physics of strong magnetic field in this particle physics context, even up to the quantum gravity regime. The physical motivation, there must be reason when we study and when we publish paper about physics, there must be physical motivation. That physical motivation, from my own viewpoint, recently, that is not purely theoretical curiosity, some observation. And we very well understand about Hawking phase transition and ADS-CFT and black hole chemistry in ADS space. Actually, ADS space has the property of confining particle, so it provides kind of pressure. So actually that complete thermodynamics. So Robert Mann called it black hole chemistry because of pressure. Otherwise, that's not complete. But from other viewpoint, from cosmology and astrophysics viewpoint, we are interested in the magnetic field. What is the origin of magnetic field in the universe? Cosmic scale magnetic field, nano-Gauss, the cross the intergalactic.
Currently, actually, instead of VDP, actually PDV.
Oh, PDV. Okay, thank you. PDS, PDV.
Common
Yeah,
expression is
PDV. Yeah, tipo. All right. Yeah. Thank you for correcting. That is the one of the open question about the magnetical genesis. And from particle physics viewpoint, we have monopoles, just because the standard the particle physics model predict the monopoles from gauge theory, or we may just assume there are monopole. This monopole play a role for primordial black hole formation, and also primordial black hole might have captured some of the monopole to have magnetized primordial black hole. Just people call that magnetized or magnetic black hole. That is one of the possible ways for black hole to have the magnetic field or magnetized. Actually, the monopole is stable against the monopole and anti-monopole pair creation, just because the coupling though strong, but the mass increased by a huge factor. So when you look at this negative sign, mass square of coupling constant times magnetic field strength. Now coupling constant increase, so it somehow enhanced the emission of monopole pair. However, in particle physics model, actually mass of monopole really increased much large factor than the particle, the charged particle. That is the reason monopoles are safe until we have really huge magnetic field just beyond almost imagination. Now there are some models that combined the dark QED. So just assume our particle physics model has another copy, dark sector, dark QED, and dark charges, and weakly interacting dark charge can be upgraded into the black hole to have charged primordial black hole. But in our standard model, just because of a huge gap between disparity between gravitational interaction and electrostatic repulsion, direct gravitational collapse does not guarantee charged black hole. except for very tiny amount of charges. However, in this dark QED model, because the electrocoupling of these dark charges with dark photon very small, almost the same strength as gravitational interaction. So black hole can, there may be some dark charged primordial black hole. That is one motivation. The other, these two, actually that is, I'll go to that later in detail. And electric weak symmetry restoration of magnetic black hole that are suggested by Maldacena. Actually, just imagine we have primordial black hole with monopole charges. So it has very strong magnetic field on the horizon that restore electroweak symmetry. That is what he suggested. So many motivation. And Stefano just work on the signature of dark matter in magnetized black hole binaries. So that raised my interest about this study. Now, this is the first part. Now let me explain about theoretical black hole with electric and or magnetic charge. You know that, and I believe that most of the researchers here at CCAST or Sogan, they work on this theoretical black hole physics, not astrophysical black hole. So this is summary in 4 dimension. I did not talk about other dimension. Actually, that is the Einstein-Maxwell theory. In de Sitter or anti-de Sitter, then black hole can have a mass charge, electric charge or magnetic charge, and angular momentum or spin, and radius of ds or ads or lambda. Now, by turning off some of the pairs, we can have the Kerr-Newman black hole in Minkowski space or the RM black hole in ADS. And the final one, just turning off the angular momentum and in Minkowski, asymptotically Minkowski space, RM black hole. Still, it has interesting features. Actually, I worked on that in the past more than a decade with my collaborator Changmei Chen. Probably he's attending, his group is attending. Actually, ionic Kerr-Newman black holes in ADS. This is the most general. Now, the charges, the electric charge has the vector potential, and the magnetic charge has dual potential. So this is configuration for rotating black hole and the electromagnetic field. So the geometry come from the solution of this black hole. The black hole solution come from Einstein-Maxwell equation with the stress and tensor, energy moment tensor from this electric charge and the magnetic charge, and just solve it. Then you obtain this most general, the 4-parameter, the black hole solution. Now, Hawking temperature, this black hole has Hawking.
What is the R subscript P?
Oh, actually, that is the kind of unphysical solution. Yeah, it has negative, unphysical mathematical. And R plus is the event horizon, the outer horizon. R minus is inner horizon or Cauchy horizon. RC for de Sitter, actually that is cosmological horizon, yes. Then RP, just because it has 4 root mathematically, but actually that is unphysical because R is a radius coordinate. Now it has the Hawking temperature, entropy, the chemical potential associated with the rotation of black hole, chemical potential for electric charge, chemical potential for monopole charges. So actually the leading Hawking radiation is given by this one. So for bosonic, the particle emission for actually it obeys the Bose-Einstein the distribution together with gray body factor. But about that, the Bose-Einstein distribution part, actually that is determined by this Hawking temperature with the chemical potential. So it looks exactly like a thermodynamical system or quantum mechanical, quantum statistical mechanical, quantum statistical system. But yes.
Clarification, could you explain about the sigma?
Oh, actually, that is a kind of Dirac string, monopole. The gauge potential that is defined in northern hemisphere and the southern hemisphere. That is the reason for sigma plus and minus.
That is necessary when we think about the magnetized black hole.
Oh, the black hole with Dirac monopole type charge. Yeah. Yes. Magnetized. Yeah. Magnetized black hole. But more the simplification occurs when we consider the near extremal just because of enhanced symmetry. The near extremal black hole means two horizons close to each other will exactly coincide. Then that is extremal black hole. There, the symmetry of underlying space-time geometry increase. So this means that we can find the solution analytically in this near horizon geometry of near extremal because of enhanced symmetry. So for static case, then there is a theorem that actually the geometry is either ADS2 or DS2 or linear space cross compact space H. And I show that later through concrete model. Actually, this is the description of near extremal black hole in ADS or DS. Now, the ionic, the RN black hole in ADS and DS has this form. That is the ionic black hole. It's a spherical symmetric system. Now, just left inner and outer horizon close to each other. Then actually that is like the magnify the space-time the region near the horizon. That is kind of looking at the horizon area using some kind of microscope, just amplified. Then the near horizon geometry, it looks like the ADS. Yeah, the first two terms, that is ADS. The second term, that is S2. So this RN black hole, near extremal RN black hole has exactly ADS2 cross S2. That is what I mentioned in the theorem for static black hole, near extremal static black hole, and the corresponding geometry. Actually, here in DS and ADS space, we have two length scale. One is the black hole scale, the other is the ADS scale, just because ADS2 geometry. So it satisfies this equation. This is the relation for ADS2 cross S2. The radius of black hole radius minus ADS radius square, inverse square, that is a constant. depending upon lambda or the ADS or DS radius and Hawking temperature, just because not exactly extreme, near extreme, then we have a small parameter B that describe deviation from extremal case. So Hawking temperature, we have tiny Hawking temperature proportional to B that divided by ADS, the ADS lattice square and chemical potential for electric charge and another chemical potential for magnetic charge. The one interesting, the final result for emission, just because near extremal or extremal black hole Hawking temperature, extremal black hole Hawking temperature is exactly zero, mathematical sense. Near extremal, as I mentioned, it has tiny, just because B is very small. So exponentially, Hawking radiation is exponentially suppressed. So for this near extremal, the RN black hole inducer or anti-inducer, actually, Changmei and I found this very universal factorization property. One factor, actually it comes from the exact solution just because, as I said, enhanced geometry in the near horizon geometry of near extremal black hole, it has a maximal symmetry already. So it allows us to solve charged Klein-Golden equation or Dirac equation. Using them, then we can second quantize and compute number of particles produced, just because there is no Hawking radiation because of extremely small, the vanishingly small Hawking temperature. So we have additional this spectra, but the first spectra come from two-dimensional ADS space. And now, just because the black hole has electric and magnetic charges, so the electric field and the magnetic field from magnetic monopole actually it radially direct to space infinity. So this is the 3D electric field or magnetic field on the horizon. Actually, that is the ADS2 geometry. That is the 3D, actually, exact result. And we have an additional factor just because now near extremal black hole, we have extremely small, though, the Hawking temperature. So we have that. Now, just because of that, that is not exactly the other type, Lindler, very close to Lindler space. So that is the Schwinger impact with the chemical potential. Now, interesting feature is that all this emission formula is described by effective temperature. This is actually the unknown temperature for acceleration of electric and magnetic charge for diodes. Then combination of these two. For electric charge, just neglect about the magnetic charge down. Actually, that is the acceleration of electric charge by electric field on the horizon. That is the unknown temperature associated to acceleration. This is the ADS2, two-dimensional scalar curvature. This is the effect mass. When put all this quantity down, it has this simple factorization. So far, we have checked this universal factorization property, most of black hole in 4 dimensions.
Well, why did you think of TU?
Oh, acceleration.
So actually, accelerated particle
Accelerating charge, yes.
in the unknown temperature.
Yes.
We have to think of accelerated observer instead of accelerated particle.
Oh, accelerating particle.
Accelerated particle.
Measured by observer at infinity. Yeah,
accelerated particle.
yes, yes. Hard acceleration, yes.
But observer is, where is observer?
Infinity,
Infinity.
detector at infinity. Oh, this means that the charged particle emitted from black hole horizon actually, that is the measure by an observer at infinity. I'll skip all these. This is the ionic K black hole. It has the angular momentum is a little bit more complicated than simple than black hole, but actually similar structure. The Hawking temperature, entropy, chemical potentials, etc. Now, near extreme of ionic black hole, Kn black hole, it has the Hawking temperature, chemical potential, and chemical potential for electric charge, chemical potential for magnetic charges.
I'm very simple. In the space, the entropy. Yeah, I'm sorry.
This?
The geometry, yeah. So the geometry has been string-like object due to the existence of the sigma.
Yes.
So in that case, the
That
entropy, is there any confusion? There is no confusion from the object in the entropy formula?
Oh, actually, it is independent. Only actually the charge, electric charge and magnetic charge enter here. Implicitly, the A and the sigma, it depends on the spin and the radius of
Question, where can I find sigma here?
sigma. This.
No, small
Small
sigma.
sigma.
Oh, actually, that is the direct monopole is defined not the whole sphere one time, just cut northern the hemisphere and southern hemisphere and just glue it. That sigma plus and minus implies.
So that small sigma does not affect the black hole geometry you're talking about now?
No, it only affects the vector potential and
Only the vector.
dual vector potential. It has two. One, this one for charge, the electric charge. The other is for magnetic counterpart. So if now we have a universal the picture. Now the same. Now we have the angular momentum, the black hole entering from quite a similar structure, more complicated though, but the same structure. But this is now, yes.
So in this case, you are saying that there is no Hawking radiation, but there is a particle creation by Schrödinger.
Oh, yes, electric field and the magnetic field on the horizon. Hawking temperature just suppressed to by exponential factor. Exponentially suppressed only. But near extremal one, you see that the Hawking temperature contribute exponentially suppressed factor. So for zero Hawking temperature extreme case, down all this term goes to zero. Now this cancels, and you have only the Schwinger effect in ADS2. That is the case for extremal Km black hole in DS and ADS. However, near extremal means that the two horizons very close to each other, and the Hawking temperature therefore very small.
So this Schrödinger effect only occurs near extremal region.
Oh yes, horizon. Yeah, horizon. Yeah, near horizon, yes. We just second quantized charged particle near the horizon.
Then, and what's the net temperature?
Oh,
So you have two temperatures, TS and TS.
oh, actually, yeah, good, yeah, good question, thank you. These days, people say, what the super question, what, yeah. Anyway, just because this is the kind of some reading high temperature. Now, when you have thermodynamical system with a higher temperature that dominate than zero temperature or lower temperature. Actually, there is this one has positive sign. This has negative sign. This one is smaller. Actually, when you compute, then this is much smaller than this one. So actually, this term dominate. Yeah, this temperature dominate. But when you compute the compute 3D in de Sitter or anti-de Sitter, this is the case in anti-de Sitter in 2 dimensions. Then exact formula has this structure. And if you ask the origin why we have this small, the additional factor, that is really good physical question. I know only mathematically, but actually Changmei asked the same question as you did, but we discussed this problem, why we have such a difference between DS2 and ADS2. That is actually come from the boundary condition. In the global coordinate of the Sitter were non-static, the expanding the space-time geometry for de Sitter, the boundary condition for quantum field theory. The solution does not give you all this, the second quantized information. You apply the boundary condition in vacuum and out vacuum, but the problem becomes scattering, quantum mechanical scattering of the barrier. Coming from the DS2 geometry. On the other hand, for ADS2, actually the same the quantum field theory, actually that is the boundary condition for quantum tunneling. So there is kind of some this very strange behavior appearing. Yeah. In strong field 3D.
Which temperature is the real temperature you measure in laboratory?
Oh, actually, yeah, this one. This is the leading term. This is minor
or
term.
T tilde?
Yeah.
T or T tilde? Which one is a real physical temperature?
Oh, yeah. This is the effective temperature.
T tilde?
No.
No.
What? That is
What is
small.
small?
This is the leading term. Yeah. This is the leading term.
bigger one is physical.
This is the real observable.
Yeah.
If you have the charge detector at infinity, special infinity, you measure this leading term. All other terms are exponentially suppressed. This term, much suppressed than this term. So your charge detector located at the special infinity will measure this Boltzmann type distribution. Yeah. You may be interested in this Mariai black hole just because recently Changmei and his group, his two students, one of them is undergraduate student. He joined this project when he was a junior. Now he's a senior. Now we are preparing the second paper on rotating black hole. Actually, in the Sitter space, we have 3 horizons. Inner horizon, that is Cauchy horizon, black hole horizon, outer horizon and cosmological horizon. Now, there is another way to make coincident or to make two horizons close to each other instead of inner and outer horizon and cosmological horizon close to each other. That is Nariai black hole.
Very simple question for the Nariai black hole.
Yes.
So when you think about the Nariai black hole, we could not think about the radial direction of the whole space-time. So the Schwinger effect was the particles propagating well.
Oh, yeah, good question. That is why we are studying near, not exactly overlapping. Near. Yeah, yeah. Yeah, good. Yeah, thank you. Actually, yeah. Right.
But I have a comment.
Yes.
In the coincidence of two horizons,
Yes.
actually that's for actually coordinate system. In real top length,
Yes.
it's non-zero.
Yes. Yes.
That
yes.
is the Nariai.
Yeah.
So in that sense, you can measure in that region.
Yeah.
Yeah.
But
Just the coordinate are coincident, but
Mhm.
your
proper length.
proper
yeah.
length is
Mhm.
non-zero.
Yeah.
That is the Nariai.
So it can be anything, the proper length.
No, actually.
Not-zero.
Yeah, but, okay, but from physical point of view.
The distance measured by,
Any proper length.
yeah,
It's
Pretty
two
falling
points.
observer, yeah.
Non-zero.
yeah, pre-reporting the inertial observer measure that proper length. Now, the extreme RN black hole, the system it has a S2 cross S2. That I explained. Now, Nariai black hole, that the black hole horizon, outer horizon, and the cosmological horizon are close to each other, then the geometry it changes. S2 cross S2, and this attracts one of the issue in string committee, just because this Nariai black hole looks like a kind of very specific 3D, the 3D system. Now, the geometry changes S2 cross S2. So this is the event horizon, cosmological horizon. Now, this region, time-like, we call inner. And this is time direction changes, so space-like. So the role of coordinate, the time and the space reversed. So it has the near horizon geometry, but in the outer, just beyond cosmological horizon, now how actually that come from the radial coordinate now play the role of time. Actually, so the metric, two-dimensional metric, then looks like expanding because of tau, like expanding the geometry. So the quantum field theory become time-dependent. The Klein-Gordon equation or the Dirac equation. This is the S2. In time, like inner region between two horizons, then actually it looks like a static. The sector, the geometry. So quantum field theory becomes space-like. So, and the Hawking temperature and the chemical potential, putting all this, and after doing some computation, this is actually the calculation rate, mean number in the outer region. Actually, it has this form. Actually, that is a 3D problem in DS2. Very interesting point. that come from the denominator of second factor for near extremal. Now it cannot happen for black hole, though it looks like Hawking radiation, but actually Hawking radiation, you cannot extrapolate Hawking radiation the formula to extremal just because geometry changes too. That I described already, and I emphasized many times. So you cannot extrapolate the Hawking formula, but here, the near extremal black hole, near horizon, because of the enhanced symmetry. Anyway, now it has this Boltzmann type, the vector, Boltzmann type distribution vector. Actually, it is very interesting just because of we can have bosonic condensation like catastrophic emission when K is the separation quantum number. Now that is energy like parameter. So the energy minus chemical potential much less than Hawking temperature. Though Hawking temperature though small, when these conditions satisfied, then actually denominator very small. Yeah, become very small. So we have catastrophic emission. Actually, this is we just wrote down the equation down when I did this winter, during the winter break, May, then we discussed about and try to find the physical meaning why we have catastrophic emission. This means that actually electric field beyond cosmological horizon actually it decayed rapidly because of this bosonic condensation like catastrophic emission. So de Sitter space become purely de Sitter without the electric field. That is what we have observed this winter. Now in the inner region, as you see, there is no such a kind of bosonic condensation. On the other hand, we have the exponential amplification factor. When just because Hawking temperature is small, now omega minus the chemical potential for electric charge. So we have amplification factor. Now, the reason why we have a bosonic kind of the condensation or bosonic type distribution here, it looks like a fermionic type. The reason is, as I said, when I answered to Moin, actually boundary condition give entirely two different behavior. So by comparing this, the mean number in the inner region with the outer region just beyond the cosmological horizon, then actually it reverse, inverse of each other. You see that in the previous slide. You have negative sign, but in between now you have the positive sign. This one looks like fermionic. Fermionic distribution line. The reason is the boundary condition I explained. Now, Stefan is more interested in the magnetized black hole, but actually, I have only 5 minutes. The electrovacuum solution in Einstein-Maxwell theory, there after lots of the formalism and computation, you find this one, that called the Robinson universe. Actually, that is the geometry in uniform magnetic field that extends the whole space. Actually, so it has kind of the the charge over, that is the field strength. Now, so this is non-singular spherically symmetric and homogeneous, the Einstein-Maxwell solution, Maxwell equation. And this is the null tetrad formalism in Newman-Penrose formalism. Actually, use this one down the Newman-Penrose formalism actually complex scalar potential for Maxwell part that is given by that one. But this is not the obvious just because you can transform to other coordinate down after this coordinate transformation. You will see that it looks like what? De Sitter, sorry, anti-De Sitter, A cross S2. So the Einstein-Maxwell solution has this topology. This is a global solution with A boundary, asymptotically A boundary. That is not physical. Actually, if we are interested in the applying the black hole to the real astrophysical system, then just because this black hole, the solution, this black hole solution has uniform magnetic field, it extends the whole. So some people just name it black hole in magnetized universe, uniform magnetic field and black hole. In that background, that is the Robinson solution. Yeah.
Simple question in previous page. Q square is in front of the angle.
Yes.
It's not different from the R and it's related.
Wow. So this is a parameter in the coordinate transformation. If Q is not equal to 1, now you have two length scale. One is the ADS radius, the other is the black hole size. So not equal. This you have seen from the RN black hole in ADS space or DS space. Actually, this is a summary of the special space-time that is given by product of two parts. The one of them actually that is parameterized metric for all direct product space, actually 2 by 2, two-dimensional subspace and two-dimensional subspace. Then null tetrad formalism. Then actually Newman-Penrose, the scalars. This is about the scalar curvature of Ricci, the Ricci tensor. It describes that part. I1 that describe the Maxwell part. Anyway, then can classify. It has only this part, only one of them, that these two cross S2, Mariai black hole, then ADS2 cross S2, N-type Mariai, and ADS2 cross S2, that is that 40 Robinson. In this table, all can be summarized. What remaining is the two-dimensional compact manifold. So we classify all of them. And now I do not have time to go to that magnetic black hole. Actually, you are interested, and your group is interested. Now let me go to the conclusion instead of actually. Stefano and I attended the GLW meeting in Yerevan last June. Then we attended together the Italian-Korean symposium. Yeah. One also attended that. There are some discussion about these things. Now, actually challenges. Rotating black hole surrounded by charged plasma, ion plasma, and electromagnetic field may provide central engine for GRB. Now, this is kind of the well-accepted model to explain GRB. And the black hole was awarded the Shaw Prize for this contribution. Central engine for GRB, gamma ray burst. And the Shaw Prize is more than Nobel Prize, prize money, actually. That is for mostly given to mathematicians or astronomers. So very interesting, just because it provides a kind of central engine for one of the mysterious astrophysical phenomena, GRB. Now, from the theoretical viewpoint, from general relativity viewpoint, actually, the story is unfinished, incomplete. We just say incomplete, yeah. Now, the GS MHD equation, that is the magnetohydrodynamics equation. That is the environment of black hole. That is what so far astronomers have observed looking at the signals from black hole. So it must incorporate MHD. Now GSE equation in core black hole, actually the assumption in this context is that rotating space-time geometry, now it has the killing vector coming from the rotation. This rotational symmetric killing vector, actually, that is the exactly guarantee magnetic field. So in that axisymmetric space-time geometry, actually, we can have a magnetic field. It kind of like the yes. So in the given rotating black hole space-time geometry, just write down the MHD equation we call GS equation. For instance, Ponsley extensively studied this system for 50 years or 40 years. Now, Ioka and Misao Sasaki, he was Misao's former student, and his thesis about that. Now, the comprehensive review article by Baskin about the accretion disk and the magnetosphere, combining GS equation in this rotating space-time geometry. Now, I'd like to raise a kind of challenging problem to young people, find analytic solution for Einstein-Maxwell equation. This is not a solution of Einstein-Maxwell equation. Given rotating space-time geometry and find Maxwell field, then respect this rotating space-time geometry, killing vector, rotating killing vector, etc. So here it assumes the energy density or energy moment tensor from magnetic field, electromagnetic field is much smaller. And also assume that the plasma density is smaller than actually energy moment tensor, energy momentum density from electromagnetic field. So gravity is strong, gravity is a major factor, so that it determine rotating space-time geometry first. Now in that, the background, find electromagnetic field that respect the symmetry. The Maxwell equation should respect the underlying space-time symmetry. And the origin of that, the electromagnetic field is plasma here. Now the charged plasma ions So this is a kind of a weakly magnetized black hole solution with less dense plasma. Now, it will be great, even more greater than the core Riemann black hole solution, to have analytic or explicit solution for Einstein-Maxwell equation with localized magnetic field or electric field. Astrophysicists need this solution just because without them, just approximation, the weak field limit. That is a kind of some like approximate solution. Now, but according to No-Hair theorem, only monopole charges. Nobody proved that actually we need kind of some the multipolar magnetic field, whether just disapprove that rotating black hole cannot have a multipolar magnetic field. But anyway, our observation just confirmed that black holes are surrounded by this ion plasma and the magnetic field up to 10 to the 8 Gauss or 6 Gauss. Pretty strong, pretty strong. We have that. Now, what is the Einstein-Maxwell solution for them? And the simple approximating approach is rotating the black hole, black hole slowly, and add the weak magnetic field so that magnetic fields can exist. Well, rotating black hole, actually, I skip many slides, and the section about the magnetized black hole, actually, there is a wild magnetic field that respects the axial symmetry, the killing vector from axial symmetry. So rotating black hole allow this wild magnetic field. Well, the slowly rotating magnetic, the Schwarzschild type black hole can have some weakly magnetic, weak magnetic field. More challenge actually, as I said, the black hole, because of No-Hair theorem, looks simple, much simple. I didn't realize that actually black holes are the most simplest solution, analytic the solution of space-time for compact object. Just because we have more than 30 magnetars. We have a few thousand highly magnetized neutron stars. That is observation. And about the magnetar, the Vicky Kaspi was also awarded the Shaw Prize. Actually, that is the prize from Shaw Foundation in Hong Kong for discovery of magnetar. She and her collaborator, they identified about 30 magnetars. The highly magnetized neutron star with magnetic field stronger, higher than 10 to the 13 Gauss. Now this is the real astrophysical object, compact object. Now, what is the geometry, general relativity geometry, space-time geometry? Incorporating equation of state, nuclear equation of state, and also strong magnetic field. And it turns out that magnetic field has more structure, not simply dipole type, it is multipolar. So do we find the geometry or space-time solution for that? Just G mu nu equal to T mu nu. In T mu nu, equation of state and including energy moment tensor for strong field. That will be kind of a historical discovery, more important than complex solution in astrophysics and astronomy, just because we have so many data, observational data from rotating black hole with magnetic field. So this is the conclusion of my talk. Actually, this is a challenge for young people. If we find a solution, then I'll be very, very happy to write 20 pages of Wikipedia covering this solution, applying to various astrophysics, just because actually there's some limitation in applying this approximate solution to real, just because what happens when magnetic field, the energy momentum density tensor cannot be neglected. How this affect? If you are equipped with mathematical method, will just disapprove existence of this kind of solution. That will be great. Yeah, that will be great. These days, during the pandemic period, a few mathematicians just showed stability of Einstein equation of the second order. The proof is almost 1,000 pages, like a book. Yeah, second order, not linear perturbation, non-linear perturbation, a few hundred pages at least. Yeah. So I want to finish my talk by telling you these two. This is maybe more simpler than now, but real physics must describe by the last lines. Yeah, thank you.
This is questions.
Yeah, simple question. Imagine is any neutron star or magnet without a fusion but with relativity. I'm guessing.
Then how do we observe non-rotating highly magnetized neutron star? That is another question. Just because, yeah, pulsar mechanism actually that come from the spinning or rotating magneton. Otherwise, non-rotating, then there is no induced electric field that actually explain all kind of emission, synchrotron radiation, curvature radiation, and others. Now you have a static magnetic field down. What will they trigger emission of charged particle into the magnetosphere? Actually, that is the origin for synchrotron radiation and other emission of radiation. So non-rotating highly magnetized neutron star or magnetar will be theoretically interesting, but actually no way to observe. Yeah. Yes.
In your first part of your talk, you have explained the quantum effect.
Yes.
And,
Yes.
and in the conclusion, it seems to me that you have just mentioned classical. So
Actually.
what is the relation?
Nothing.
Your first part and the second
Just
part?
because, yeah. Thank you pointing out. Actually, my talk consists of two parts. One is as I told you at the beginning, theoretical part, and I said researchers here at Sequest or Sogan, they're interested in theoretical black hole, not astrophysical part. But I skip all these things. Sorry. So expecting not much time, I just summarize only the second part. That is what I expected, just because my slide more about the 40 pages, but actually less than 15 pages, well, about 15 pages enough for 1 hour. I talk a lot, and you ask many questions. That is the reason why when I cover, actually Stefano and Arapam and Tomi will be more interested in that part, and I'll go to your group room, your office, and explain about them, just because you asked many questions this morning and this afternoon. Yeah, about he's not interested in theoretical part. He's interested in this magnetized black hole. Yeah. So
Yeah, the problem is that the astrophysical approach
Yes.
is kind of complementary.
Yeah.
And when you study a specific black hole astrophysical object,
yes,
everything is determined by the local conditions.
yes,
You have an accretion disk,
yes.
you have some plasma creating on the black hole. For instance, the magnetic fields that you show in your equations, they are just the solutions of the Einstein equation
Yes.
based on some symmetry
solution.
and so on.
Yeah.
But for instance, these black holes are coherent on the scale of the physical object.
Yes.
But when you study the plasma
Yes.
of a real object,
Yes.
what you get are magnetic fields which are incoherent, they are chaotic. So
many. Yeah.
you solve the
Yeah.
diffusion equation typically.
Yeah.
And so really the approach, you don't really care about all this because also the region where the magnetic field can create an observable, how do you measure a magnetic field? You have to measure some synchrotron radiation.
Indirectly.
Because you have to measure it. If you want to do some phenomenology, you have to measure it. Now, the problem is that in the plasma, when you have an accretion disk, part of the plasma is thick. That means that does not emit anything, just the thermal black hole radiation.
Yes.
And so you really need, usually if you have a synchrotron emission, there are some systems where you really can try to fit the data.
Yes.
But you have to assume that you have a region where the flux, the accretion, is not thermalized. Is not thick. The plasma is not thick because otherwise nothing comes out.
Yes.
And so you have to assume that you have an accretion which is dominated by advection.
Yeah.
And this means a completely different physics for that. So you really have to make a model where you have to make assumptions about whether you are equal partition or not.
Yeah.
So at the end of the day, you work in just a flat space-time. You don't care about general relativity. Maybe you can make some corrections. But so at the end of the day, I was trying to understand this morning, we discussed whether we can really, we have to find some physical system for which this can be applicable. But it depends on the physical system, because in astrophysics, when you try to fit the data on a black hole binary, for instance, or on a system on an X-ray binary, for instance, the physics is completely different from that.
Oh yeah,
You
I
really-
agree.
You can, when people try, when astrophysicists try to explain the data,
Okay.
not a single of the equations that you showed today appear.
Yeah, no objection to your
Yeah,
argument,
no, so it's difficult to find a common approach.
Stefano, you know, to have your Sagan model for dark matter observation from the sky, then you need very solid theoretical framework to model. That is this one. I saw that this morning, and now I repeat again once more. Call rotating geometry.
Yes.
You need a Sagan model for dark matter, the astro astronomical or astrophysical observation, actually.
나리아.
Rotating black hole.
나리아 limits.
Yeah.
Okay?
나리아 limits.
It is very, exactly.
Yeah. Yeah. So just base your model on this. That's it. Then just apply that to your model to compute the dark matter interaction with plasma or others. Now,
Yeah, also another issue is that from the observational point of view, what you see is actually the physics of the plasma itself. For instance, in some of these binaries, you can really measure, you can really see the point where the plasma from the donor star is falling on the accretion disk.
Yes.
You have a point,
Yes.
and then you can really measure where the geometry of the system. So you
Yes.
have some experimental data
Yeah.
that allow you to make a model that is more or less realistic.
Yeah.
And instead of starting from symmetries,
Yeah.
this is the only symmetry that you can think of, of course, is an axial symmetry.
Yeah.
Apart from that, there's not much.
So what you need is MHD. The plasma just provides sources for Maxwell theory in this rotating black. That
can come from
governed by coupled to plasma.
Of course, there is also the problem. The problem is also that it depends.
Yeah.
If you have where is the plasma coming from? It's coming from the formation of the black hole. So from the environment where the black hole was formed, or in the case of a binary, you have a star, and then you have accretion from the star. So every system is really different.
Yes, yes.
And so it's not easy to just write an equation based on some symmetry, because this is very nice from the theoretical point of view, but then you need to do some comparison with this.
So this is the Maxwell field, and your plasma just generate this Maxwell field.
This Maxwell field is coherent on the scale of the system.
Oh, yes,
So
but actually,
in the plasma, when the particles produce the magnetic field, either if you have a thick plasma, you don't measure it. You just measure the thermal emission from the surface. If you want to measure something that can tell you what is the magnetic field inside the system,
yes,
you need to have a detailed model of the region of the plasma of the accretion disk where you have a thin disk.
yeah,
So you have to you have a system where basically the particles are moving like you have convection or advection, whatever,
yes,
and they are. So it's what you expect is not a magnetic field which is coherent, like a big dipole.
yeah,
But a chaotic magnetic field, a magnetic field that the average is zero. That B square, the average of B square is different from zero. You understand? So it's just, and then you have a diffusion equation. So it's a completely different. It's not that magnetic field that we have in mind when we calculate.
Actually, the plasma, the disk, actually, in a sense, can be modeled by circular current down either if this magnetic field configuration. So
of course, you can have also
large
a
scale,
magnetic field on large scale. Okay, a
large scale,
magnetic field.
yes.
But first, how do you know that the system that has it? And second, can you measure it? Because eventually, even if you have it, this magnetic field, the magnetic field is only where the particles created.
Yes, yes.
Because it's the plasma that creates magnetic field. So you can locate it experimentally.
Yes.
So typically, it's not the size of all the systems. So
I think that the gap is from like we can imagine anything in classical magnetic, classical electromagnetic field, so without shear. But this is some people who want the
I understand.
Imagine I threw the GR solution. Here is the one of the solution, the curve black hole, and considering the magnetic field in cogeometry. That is, I guess, that is something equation, solution of
Yes,
the
but you should
maximum.
find,
Yeah, but.
okay, then you should rephrase,
Yeah.
you should rephrase
Yeah.
the model that
Yeah.
starts
Yeah.
from the physics of the plasma
Yeah,
and rephrase it in terms
Yeah.
of this formulation.
Mm.
yeah, you're right.
Yeah.
Macroscopically, there are many issues, but somehow large scale, the black hole scale, this is the configuration for magnetic field, yes. Just because the large scale, in large scale, the plasma should be consistent with this magnetic field. They follow the Einstein-Maxwell, no, sorry, Maxwell equation in curved space-time. So plasma must follow in large scale, the black hole scale, this configuration. But yeah, you're right, at microscopic scale, there are many issues, kind of some interaction.
The magnetic
Yeah,
field can be chaotic at the low, at the
Yeah.
small scale.
yeah,
You understand?
yes,
So
yes.
it's
Yeah.
really, you don't have a coherence at the
Yeah.
scale of the
Large
system.
scale,
On
a
that,
small
for
scale.
instance, the magnetic field in our galaxy, the
Yeah.
electromagnetic field in our galaxy
Yes.
is, our galaxy is not a big dipole.
Uh-huh.
You just have a background of magnetic field background.
Yeah, I agree about that. The smaller scale than black hole, the size, then there must be some kind of local fluctuation of magnetic field and others, and
Yeah,
also
but
the
actually,
other
when
physics
people-
enter
when
here.
physicists try to,
Yeah.
at least in some systems, when
Yeah,
physicists try to fit the data and to interpret, for instance, the synchrotron radiation in, sorry, the radio signal in terms of the synchrotron radiation, they assume a microscopic, a fluctuating magnetic field.
So
Which is, of
this
course,
is a
a-
kind of some large scale, and
Exactly,
plus
this is
there
large
must be a
scale.
local,
And so my
small
question is,
scale
Is there a
fluctuation.
way to
Yeah.
know if a system can have this large scale?
Mhm.
Can we measure it? Can we, it's not clear to me.
So here, actually, the magnetized black hole does not care about the local fluctuation of magnetic field. You're right, yeah.
Yes.
I agree about
They are
that,
completely
yeah,
different
yeah.
situation.
Not completely different. Two different
From the-
scales,
Yeah,
yeah.
different scale. And
Yeah,
so if the physical
Yeah.
system that you're studying is on one scale, you don't
Yeah.
care about the other.
Yeah. So overall the accretion disk and the plasma, not given by that, but microscopically small scale fluctuation of magnetic field and the interaction of particle, and also the kind of some thermodynamics enter, ordinary thermodynamics enter because of the temperature.
Yes, very
Plasma has temperature, it has
exactly. You
the
use
ions, so
Hydrodynamics.
electric,
thermodynamics,
Yeah.
hydrodynamics.
Yeah.
everything.
the electron, average thermal velocity is order larger than the proton thermal velocity. So actually this rotating black hole and the magnetic field play a role of generating, otherwise charge neutral, actually electron proton cannot separate except for thermal velocity difference. There must be some other the mechanism, otherwise the strong electrostatic attraction just combine again. Only small scale fluctuation, but this rotating black hole with this large scale magnetic field, actually it provides driving force to generate current. So it has kind of circular current. That is what in this committee they want to study. Actually, now I am most, and he applied this one to compute the electron positron pair and found that actually huge current. Simple model. This is a simple model and applied 3D, showing the mechanism to explain about the huge emission emission, actually chemistry training electron volt. This is the particle, high energy particle. This may be the origin. Why? Just because the rotating black hole can have magnetic field. This magnetic field and the induced electric field just because of rotation, just accelerate particle up to chemistry training. That is what almost the highest energy cosmic ray detected by ice cube. Yeah. There must be some mechanism for it. So
Okay, it's been a whole time, so we can discuss later if you want. So let's thank again, thank you.
thank you for the invitation.